Hello, let's look at motion graphs. In this case we're going to look at how we interpret displacement time graphs. A couple more examples. So we've had the theory, we've talked about it, now we're just going to work through a couple of examples. So if I showed you this graph here in class or gave it to you as a question, you'd immediately check out the axes. In this case it's time and it's displacement in meters, and you'd recognize straight away that it's a displacement time graph, and you'd remember that on a displacement time graph the slope gives you the velocity. Now I could ask you to write a paragraph describing the motion that this body undergoes in the 60 seconds described here in this graph, and you could say, well, it starts at the origin, it moves to 60 meters after 10 seconds, it stops there, and then it moves to 100 meters, and then it stops there, then it moves back to the start. And that's an okay answer, but you actually need to do a bit more than that to get the full answer. You actually would need to do some analysis. And what sort of analysis are we talking about? Well, displacement time graph, what does the slope tell us? The slope tells us the velocity. So in your description you would actually be expected to have worked out the slopes of the various sections of the graph, which I just happen to have done already. So in the first one, we draw our little triangle, do our rise over run, and we get 6 meters per second. Do this little slope here, 4 meters per second. We do this slope here, remembering that this is actually a negative slope because it's a fall. So we're doing, if you forget how to do which ones are positives and which ones are negatives, if you imagine yourself a little person again and you climb, when you're climbing it's a positive slope, when you're walking down this hill it's a negative slope. And this is minus 100 because we're going down and across. That means that's minus 5 meters per second. So all your work is done? No. You need to just make sure that you remember that there's two other velocities you need to mention. These sections here, when it's actually stationary, it's stationary at different positions, so you need to tell that. Here, for example, it's stationary at 60 meters from its start position, and here it's stationary at 100 meters from its start position. Now, is that all you have to do? No, you may be actually asked to sketch the velocity time graph for this motion. And so you need to draw your axes. Now if it's a sketch, I should have used a ruler, but I can't use a ruler on this thing, so you would have used a ruler, and you need to have some data points because you put as much data as you've actually got, but not so much that it actually crowds your story. So we've got, this will be a velocity time graph, so we've got our units and our labels. We're using the same period of time, 60 seconds. And because we've done our calculations before, we'd recognize that the largest positive value that we're going to have to plot on the vertical axis is 6, and the smallest number on the vertical axis is minus 5, so that's going to be down there. Now what does it look like when we plot it? Let's have a go. Let's do this color, and at time 0 it will be moving at 6 meters per second for 10 seconds. So we'll put that point there, and that's what it's happening there. It's then stationary for a period of time, stationary for another 10 seconds. It then has a velocity of 4 meters per second, so we've got to go up to 4 meters per second. We go to 30 seconds, down, stationary again, so we plot it on 0 velocity, and then at 40 seconds it goes down to our 5, which is about there, and so, oh, that's a bit wavy, and it goes there, and that's the end. And we can assume that it's that's the end of the time period. And so this is our velocity time graph for this motion. Now it's pretty chunky, and it looks more like an acceleration time graph, but that's not a problem because we've drawn what this graph is telling us. And it's chunky because these transitions are instantaneous, and so it instantaneously goes from 6 meters per second to 0, when in reality it would be a bit of a curve. Alright, but that's what that would look like. Hopefully you can see where I got that from. If not, rewind it and have another listen to it. Let's have a look now. Right, now on these ones, what sort of graphs have we got? Well, x is displacement. Well, could be a d or an s, but in this case it's x. And we've got t as time, so it's a displacement time graph. And what we've got to do here is we've got to interpret this graph and draw or sketch the equivalent velocity time graph for this. So what's our interpretation here? Well, it starts at a point, we could say 1 meter, and it moves away from that point at a constant rate till it reaches this point here, which is here. So what does, on a displacement time graph, what does the slope tell us? Slope tells us the velocity. And is the slope changing there? No, so it's a constant velocity and it's a positive slope, and because we're sketching it, we can just draw a line. That's probably one of my best straight lines for a long time, and that would represent this motion here. Hope we understand that. What's about the next one? A little bit trickier. Again, a displacement time graph. We've got an object starting away from the origin, and then it moves towards the origin, hits the origin, 0 position there, and then keeps moving away into negative space. So this is negative displacement. So we could say that that's positive displacement and that's negative displacement. So it's starting over there, coming towards me, then keeps going. Doesn't stop. This here is not a stop, it's just moving straight through. Now we see also that it's got a constant negative slope, and it's a little bit steeper than this one, isn't it? So we should really put it down here, and it's going to be a constant negative slope like so. A lot of students are tempted not to put negative slope here because it's in the positive region of the graph, and so it's got to be a positive slope, and you just confuse yourselves. If it's a negative slope, it's got to be a negative velocity. That's the rules. Let's do one more, a trickier one, a slightly extension one. And in this case, we're given the velocity time graph, and you've got to do the displacement time graph. And what sort of motion does this describe? We've got a velocity that's changing, and the rate it's changing is constant because it's a straight line. Now on a velocity time graph, if you've got a changing velocity, what does that mean? Acceleration. And so if we could work out the slope of that line, that would be accelerating. Now what happens with displacement on a velocity time graph? Well, the displacement is the area under the graph, and so you can see that this area here is increasing with time. What does that mean for a displacement time graph? Well, it can't be a straight line. Now it's starting in negative space, and all that means is it's starting over there to my left, and it's going to move towards me and then into positive space on my right. If I'm saying that my right is positive and my left is negative. So it's starting. It can start anywhere. It could have started there, could have started there. It all depends on where we position it. But it means that it can't have a constant changing of its displacement because it's accelerating and its velocity is increasing. So it's got to start, and it's got to have a curve that gets progressively steeper. Not the best drawing, but it's going to be a curve. Because for those of you that do maths, the tangent here, which I'm drawing in red, okay, a tangent is a straight line that just touches the curve. You can derive it mathematically, but you can see that these three tangents, the slope is getting steeper because the velocity is increasing, and so that's what we're trying to represent here. That's an extension one. Okay, if you understand it, that's fantastic. If I've confused you, that's not so good. But you don't really expect you to get those sorts of questions. Now, we've got some puzzles for you. What does this graph describe? Well, what we've got here is a displacement time graph, and we've got all these lines that describe motions, and they're all labelled. So what we have to do is answer these questions. Two objects start from the same position but at different times. Which lines would represent that? Two objects start from the same position at the same time. Which lines would represent that? Two objects are travelling at the same speed as each other but with different velocities. And two objects are moving towards each other for the whole period shown. I think that's it. There might be one more. Better be ready to bring it back. Yes. Phew. An object that has a lower speed than of all the other objects. Now what I want you to do is perhaps pause this and work out which of those lines correspond to these questions. Okay, so pause it. What I'm going to do is also talk through and work it out, and then we'll show you the answers. So you could pause it now if you haven't already, but if you have already paused it, you don't need to pause it again if you've worked out the answers, if you get what I mean. Whatever. So let's have a look at it. Two objects start from the same position but at different times. Now this is position, so if you had the same position, no other object starts at this position, so the answer to this would be B and C, or D and C. Alright, they wouldn't be B and D because they start at the same time. Two objects start from the same position at the same time. Well, there we go. B and D, they both start here. Two objects are travelling at the same speed as each other, but with different velocities. Now that means they would have the same degree of slope, but because they're different velocities, one must be positive and one must be negative. Tricky. And so your answer there is A and E. They've got the same degree of slope, but one's positive and one's negative. So this might be minus 10 and this might be positive 10 slope. Two objects are moving towards each other for the whole period shown on the graph. Again, that would be A and E are moving towards each other. An object that has a lower speed than that of all the other objects. Now speed would be a measure of slope, and in terms of the lowest slope, even though that's a negative slope, in terms of speed it doesn't have a negative, so that's quite a steep slope. This is the shallowest slope, so the answer there is D. Let's just check it. Phew, I think I got them right. Hope you got them right too. Okay. And in the next video we'll do some interpreting of velocity time examples. See ya.